Greetings, class. This set of slides will be discussing about the third mode of heat transfer, which is radiation. Okay, so allow me to share my screen. So now we'll be talking about heat transfer by radiation, and first we're going to discuss the nature of heat transfer. So in here, the material is not being heated. So the medium through which heat is transferred to or from is not being heated in this case. And the transfer of heat is by electromagnetic waves. Now, the behavior of these electromagnetic waves is similar to that of X-ray, light waves, gamma rays, and so on. And they are only differing on their wavelengths. Now, this radiation or these electromagnetic waves travels in straight lines and can be transmitted through space and even vacuum. Now, most of the time, radiative heat transfer occurs in combination with conduction and convection. Now, if the problem is silent about you neglecting conductive and convective heat transfer, you are to account for all three. Anyways, you will still see if you are provided the choices whether the values that are given you are simply only accounting for radiative heat transfer or a combination of convective and radiative heat transfer, all three. So my suggestion is you account for the three and then base your answer, your best answer on the choices that are provided in your problem. Even if you're doing an open-ended problem, you're trying to find the solution to it, still account for the three modes of heat transfer based on your analysis of the problem. You need not account only for that particular mode of heat transfer if the problem assumes that its value is negligible compared to the other mode of heat transfer that is being mentioned. Okay, so let us proceed. Now, the thermal energy here of a hot source is converted into energy in the form of electromagnetic radiation waves. And then these waves travel through the intervening space in straight lines and strike the cold object. Now, the electromagnetic waves that strike the object are absorbed by the object and converted back to thermal energy or heat, or is even, shall we say, emitted back in the form of thermal energy or heat. So take note of how this thermal energy or how these electromagnetic radiation waves travel in space. So it's in straight lines. Now, for the absorptivity and for black bodies, so we have black bodies actually, and we have gray bodies, and we have even opaque bodies. So for an opaque body, the alpha and the rho is equal to 1 at all times. So your alpha is the absorptivity. So the fraction that was absorbed by the body, the amount of heat that is transmitted to the body, and that fraction that was absorbed is its absorptivity. As for reflectivity, so it's the fraction that is being reflected. So the thermal energy that is where your body is subjected to is absorbed by the body, and part of that is being reflected. The sum of the fractions of these two, absorptivity and reflectivity for an opaque body, is equal to 1. Now, what about a black body? So a black body absorbs all radiant energy and reflects none, although it also emits radiation. So it may emit radiation, but it absorbs all the energy that is, shall I say, in which it is subjected to, and reflects none of it. Now, its alpha then, if it's going to absorb all radiant energy, is 1.0. Reflectivity would be a 0 because it reflects none. And in this case, emissivity is also 1.0. This is for a perfect black body. Perfect in the sense that all energy in which it is placed into, or all energy available for it to absorb, it's able to absorb depending on the environment in which it is placed into. Now, we can attribute to Joseph Stefan as late as 1879 the formula that we are using, or the basic formula that we are using to account for the total radiation emission of a particular object or material per unit time and area. So this is rate of emission per unit area. So this is over all wavelengths and in all directions, but still in straight line mode. Okay, so this is our formula: emitted radiation per unit time and area. So you have in this formula the constant we call the Stefan-Boltzmann constant. You have encountered this in your physics, value of which is 5.67 times 10 raised to negative 8 watt per square meter Kelvin to the fourth. Now you have also its equivalent here in the English set of units. So 0.1714 times 10 raised to negative 8 BTU per hour per feet squared per degree Rankine raised to the fourth. Now this particular equation that is shown to you is the basic equation for radiation or radiative heat transfer. Okay, we owe it, or we attribute it, to Joseph Stefan. Now there was a mention of the opaque body here in the previous slide and the black body. What about gray bodies? So all bodies have emissivity and absorptivity which are equal at the same temperature. So for these gray bodies, we say that their emissivity and their absorptivity are equal at the same temperature. For gray bodies, the emissivity is always less than 1. It follows that their emissivity, the emissivity is also less than 1. Now, emissivity for highly oxidized metal surfaces is, for oxidized metal surfaces is high, and low for polished metal surfaces. So for non-metals, we expect that this particular emissivity will be high, but nonetheless, it's still less than 1.0. Unless otherwise, the problem says so that your emissivity is equal to 1.0, or that you have a perfect black body. Otherwise, if the problem is not stating that you have a perfect black body, then everything is classified under gray bodies, in which this emissivity is less than 1, equivalent also to its absorptivity. Now, here are a list of materials and their corresponding emissivities. So if we have polished silver, you have 0.02, and polished copper is 0.03, and polished gold is 0.03 as well. Now, if you're going to compare the value of emissivities for the same material, which is polished and oxidized, so notice that for the oxidized material, the emissivity is higher. Just like what is stated in the previous slide, that for oxidized material, emissivity is high. Okay, so for brass, you have this value. And for copper, you have something to compare it to as well. And you have here for iron, polished, oxidized, and the one that is plated with tin. And we have also here for lead and stainless steel, which is polished and oxidized. So oxidized materials tend to have higher emissivity over their counterparts, which is not oxidized, or shall we say that are polished. Now, problems concerning the application of the basic formula that was given to us by Stefan Boltzmann are very straightforward in terms of how we're going to apply the values to it. As long as we know what particular parameter in the formula represents, then all the rest is just a substitution to the given formula. So we'll start with this radiation to a metal tube. So a small, take note, oxidized horizontal tube, metal tube with an outer diameter of 0.0254 meters, 0.61 meters long, and with a surface temperature at 588 Kelvin is in a very large furnace enclosure. So it's inside a furnace with the fire brick walls and the surrounding air at 1088 Kelvin. Now, the emissivity of this tube is 0.60 at the temperature of the surroundings, the furnace where it is placed into, and 0.46 at 588. This is based on the temperature of the tube. So we are to calculate the heat transfer to the tube by radiation using both the SI and the English units. Okay. Now our tube here, temperature. So if you're going to read your book by John Copley's, the temperature of the material in which we are to account radiation is represented by T sub 1. Okay, capital T sub 1. The temperature of the surroundings in which that material is placed into is T sub 2. So since the large furnace surroundings are very large compared to the small enclosed tube, so the surroundings, even if gray, we view from the position of the small body, appear to be black, meaning our furnace is black, but our tube is a gray body. And in this case, the equation given in John Copley's 4.10-6 is applicable. So we need to substitute the values to that particular formula. Now, let me first share with you what that particular formula, equation 4.10-6 in John Copley's look like. So we'll go to our board. Wait, class, ha? Let me stop sharing format. Okay, so as for that particular formula 4.6, that's 10, or 4.10, that's 6 rather. It accounts for both the amount of radiation emitted by the material and the amount of radiation that the material absorbs from the perfect black body, which is our furnace in this case. So the actual formula actually, class, is this. Let me write it. Okay, so this is the actual formula in accounting for the net uh, radiation coming from the tube that is placed inside the furnace. So this is having the subscripts 1 in the first term. I'm referring to the subscripts 1 here, meaning this refers to the material or that of the tube. Well, this one, the 2, refers to that of the surroundings in which the tube is placed into. So the temperature here, the T sub 1 temperature that is placed on the first term is the temperature of the material. And the T sub 2 temperature that you are seeing here in the second term is the temperature of the furnace, or that's of the surrounding where our tube is placed into. Now these two constants here, the Stefan Boltzmann constant is the same thing with the area of the material. So we might as well factor it out since it's common. So this should be the formula that you will be using in accounting for the net rate of emission from the tube. So we have alpha 1, 2, and then we have T sub 2 raised to 4. Now, the emissivity that you are seeing here, this emissivity is the emissivity of the material based on its temperature. Okay, the temperature of the material T sub 1. The alpha 1, 2, take note, the alpha 1, 2 is the absorptivity of the material, which is equivalent to its emissivity based on the temperature of the environment. Again, this alpha 1, 2 is the absorptivity of the material. However, its value is equal to its emissivity, but not at T sub 1, but rather at T sub 2. So the actual formula that we should be using actually supposed to be in this problem would be like this. Okay. However, it is suggested that to simplify the procedure, actually this is already simple if you're going to look at it, but to simplify further the procedure of computation, you may simply have Q equal to A sub 1, and then the Stefan Boltzmann constant, and then here we will have the emissivity of the material. Now I will not label it at 1, I will not label it at 1, 2, but I will label it at 2, because the emissivity that we're going to use here is the emissivity of the material on the surrounding temperature. So actually, it's equivalent to its absorptivity subscript 1, 2 in here in the second term. So now your formula, which is actually simple in itself, is made even simpler if you're going to have this particular formula now used. So this is the formula that will be used in the solution that will be shown to you as shared in the slide. So we will go back to our slide. So take note of the formula: area, the Stefan Boltzmann constant, the emissivity at the surrounding temperature, and the two temperatures. Temperature of the material, the tube, and the temperature of the surroundings, which is the furnace. So let's go back to our slide. So if this is our slide now, the formula that I have shown to you, let me annotate, is this formula already is substituted in here already. So you have the area being the lateral surface area of the tube, which is pi dl, the length of the tube, and this is its diameter, outer or outside diameter. And then this is the corresponding value in square meter, and this is the corresponding value in feet squared. So if you're going to account for both SI and English units for our Q, now we will be having first this one, the pi times 0.0254 and the 0.61. The emissivity that was used here is the emissivity at the surrounding temperature, okay, as explained to you. And this would be your Stefan Boltzmann constant. And this in SI set of units, this is your material, the tube temperature, and this is your surrounding temperature. So in watt, this is your rate of heat transfer, the net rate of heat transfer from the tube. So its emission, as shown to you in the board as well, its emission minus its absorptivity. Okay, so you have it negative to 130 watt, meaning this is the amount of energy that your material radiates. Now, if it's in English, then you have to do is use the English set of units here, the same value for emissivity. And you use the English set of units value for the Stefan Boltzmann constant and the Rankine equivalent temperature of the Kelvin in here. So for the 588, it's 60 or 1060 Rankine, and for the 1088 Kelvin, yes, that would be 1960 Rankine. So your units, your set of units here is BTU per hour for the English set of units. So that's it. It's very straightforward, and it's even simplified because we simply use the emissivity of the material based on the surrounding temperature. Okay. Now we'll go, we will go to the next. So this is regarding radiation of small objects placed in a particular surroundings in which the heat capacity is very large. I say the heat capacity of the surface is of the furnace is very large. It's because it's the source in the first place of larger amount of energy. Now, in terms of accounting for a combined convective and radiative heat transfer to a material, it follows that you're going to use we're going to get the sum of the convective rate of heat transfer and the radiative heat rate of heat transfer rather. So for the convective rate of heat transfer, you have your H sub C. We know this is the heat transfer coefficient. We multiply it to the A, the area of the object, and this T sub 1 minus T sub 2. T sub 1 is still the temperature of the material, and T sub 2 is that of the environment. As for the rate of radiative heat transfer, then we will have the heat transfer uh, H sub R, represented by H sub R, denoting it's for radiation. And it's still A sub 1, T sub 1 minus T sub 2. If we will account first the H sub R and then plug it in this formula, then it could be solved using the formula that we have in here. So it will now be using the emissivity, the constant, the two temperatures of the material as shown in here. Now, this particular formula is best explained by the use of a particular sample problem. Okay, so we will go to the sample problem that will be using this particular formula. So in here, we have the case of a combined convective plus radiative heat transfer still from a tube. So we'll be using the example that we have, the previous example that we have. I think this is example 4.1 for combined radiative plus natural convection to the horizontal 0.0254 meter tube. Now I will go back to the slide wherein this example 4.10-1 is placed into, so that you will have recall. Oh, sorry, this is not it. Okay. Example 4.10-1. Let me check. Okay. The example 4.10-1 that is being referred to in here actually is the example I gave you in here from a different edition of the book. So let's go back to our original slide. And this is actually the example 4.10-1, because now in here we're talking about the second example, fundamental example that will illustrate the use of the formulas I introduced. So we are to recalculate the first sample problem, now this time accounting for both radiation and convection for the same tube with the same set of characteristics. So the area of our tube is still the same. That's 0.0487 using the formula pi BL. And for natural convection coefficient to the 0.0254 meter horizontal tube, the simplified equation from table 4.7-2 will be used as an approximation, even though the film temperature is quite high. So meaning we will determine the heat transfer coefficient by convective heat transfer using the simplified equation found in table 4.7-2. Let me show to you the table 4.7-2. Okay. So this is the table 4.7-2. And since we're given a horizontal cylinder, we are to assume that the product of the NGR and NPR, which we have no way of checking, falls on this range. Normally, it falls on this range 10⁻³ to 10⁻⁹. And if we're going to use the English unit, so this will be our simplified formula of determining the heat transfer coefficient. But if you're working on SI set of units, this will be our formula rather, 1.32 times the ratio of the delta T to D raised to 1/4. So this is the one that is being mentioned in the solution for determining the convective rate of heat transfer in example problem number 2. So we will go back to that. Okay, so this is the formula that was shown to you. So we will substitute the delta T. So our delta T here is the absolute difference in the surrounding temperature and in the temperature of the object. The D will be 0.0254 as stated in the problem. That's our outer diameter. And this would be the H sub C. Now, if you're going to use equation 4.10-10 and you're still going to use the emissivity at the surrounding temperature, this formula for H sub R, I will write in here na lang, paradasic, okay? So I will just annotate in this slide. The equation 4.10-10. If you're working on SI set of units, this one is equal to emissivity times the Stefan-Boltzmann constant times T sub 1 raised to 4 minus T sub 2 raised to 4. And then we divide it by T sub 1 minus T sub 2. So this is our heat transfer coefficient for radiation. So this is the value. Okay, the rest is just a substitution. So you have emissivity, you have the constant here, and you have temperatures here. Okay. Notice class that the T sub 1 temperature that is placed in here, the T sub 1 temperature, as you could see, is the temperature of the surroundings. The T sub 2 temperature is the temperature of the body. Okay. And then this one is written in this manner so that we'll get the, actually, even if we're going to interchange the two, the value that we'll be getting in here would be negative. So we're after actually the absolute difference of these two. So that is why we write first the 1088 divided by 100 followed by the 588. In here, it's the same thing. Okay. So we have this value for H sub R, and then the rest is substitution to the formula that was shown to you in the table. So in the figure, let me clear my marking. No, not the markings. If we're going to go back to the previous slide, this is the H sub R. By the way, this is T sub 2. Okay. And this is the answer to that. So if you're going to compare this one, the total amount of heat that is being transferred from the tube, if it's just pure convective radiative heat transfer without convection, then example 1, I will just keep the markings there. It's 2,130 watts. Okay, this is pure radiative heat transfer. Whereas if you account for convective heat transfer, it's 2,507. There was an addition of more than 100 or 200 to reach this one. But the thing is, its value is actually negligible if compared only to radiative heat transfer, which is 2,130. 2,130 more than 300. So if it's 2,507 in here. But again, as I've said, the value of 300 plus is not that comparable to the radiative heat transfer alone, which is 2,130. Okay, so this one simply points out to you that shall I say, the majority of the amount of heat that is being transferred by the material is more on radiative heat transfer rather than convective heat transfer, or shall I say natural convective heat transfer in this case. Okay, as I have pointed out that in here you have 2,130. Here radiation was only considered. In here we considered both. Okay. So I think this particular two sets of problems, since we are only asked to strike through the essentials and the fundamentals of the topic, that way we can cover all the topics that we should be covering for the course, would be enough. So this would suffice for the topic of radiative heat transfer. Okay, I will post the link to this in Canvas for you to listen to, and then the next topics as well. Thank you, class.